Okay, hello everybody. My name is Andrey Timokhin. I am a Pulsar theorist. And in this very short talk, I will try to. So, is it possible to get a full screen? So, in this talk, I'm going to give you a very short overview of sort of attempt done by a bunch of people trying to understand how pulsars work, starting from first principles. Okay. Interesting. Okay. Good. So basically, so the problem, everybody here knows that the pulsars are not such a simple phenomenon as people used to think, let's say, 50 years ago. It's just a rotating magnet. So what's the, so just how more complex could it get? Yes, it is a rotating magnet, but it is a much more complex system than we thought. So that the basic fact about pulsars we know now is that the radio emission for most of the pulsars, excluding TRAP, and we don't know so much about millisecond pulsars, seem to come from the regions called polar caps, so just regions pretty close to the neutron star surface if you compare it to the overall size of the magnetosphere. And the high energy emission seem to come from the outer regions of the magnetosphere. And this is not based on any theoretical assumption, it's just the empirical facts. So just, we have to deal with it. Another fact, and I'm well aware, of the results of Fermi, that some pulsars show that some pulsars seem to emit most of their spin down energy in gamma rays, but for most of the pulsars, for most of non-millisecond pulsars, the radiation, in whatever energy band, constitutes only a very tiny fraction of the total energy losses. So the pulsar machine is ideal, and the radiation is just a tiny friction. So pulsar is mostly a plasma machine. And this machine, when it has regions where the friction is working, is producing radiation. And why am I going to talk about polar caps? Is just because those regions are extremely important, at least in the current paradigm of how pulsars work. Why? If we look at the overall picture of the pulsar machine, we know that there are close magnetic field line zone in current paradigm, and which is strongly supported by empirical evidence. It seems that no radiation is generated here. Those are the dead zones. And all the plasma which is produced in the pulsar is streaming along magnetic field line and ultimately goes into the pulsar wind and produces pulsar wind nebula. And we know that pulsars do produce a lot of plasma. Again, nothing to do with theory. You look at the crop nebula, you calculate how many particles you need, and you get a number which is orders of magnitude higher than the Golden Julian charge density. So there must be a plasma production going on. So there are theoretical arguments, but it's very difficult to argue like this well-established observational facts. And if you look closely at this picture, you don't even need to look closely. All the plasma, which is carrying all the rotational energy, all the 10 to the 30 ergs, 10 to the 38 ergs per second in case of the Crab pulsar, is coming through these tiny regions, all the way to infinity. So what is happening in polar caps affects the whole pulsar machinery. So those are extremely important regions. So just in case of crabs, so those regions are like a kilometer or give or take some in size. And the whole magnetosphere up to the less than 1,500 kilometers. And all these 10 to the 38 ergs per second are coming through these regions. So we have to understand what is going on there. Moreover, so just if you look at a pulsar as an electrical circuit, so what is going on? So this is an ideal magnet, and this magnet is sort of wired through plasma, flowing along magnetic lines to infinity, and that's how it loses its energy. The whole current system is ending up in the polar cap again. So the current flows away and comes back. Everything goes through the polar cap. We don't understand how polar caps works. seriously. So just we shouldn't consider our investigation of how the whole magnetosphere works unless we understand what is going on here. Because if these regions, for instance, fail to produce enough pairs, there will be no plasma field magnetosphere. This picture is closed and open magnetic field lines, I hope you realize it exists only because pulsar is surrounded by plasma. No plasma, no open closed magnetic field line, no other concept we have. So we have to understand how this tiny region works. So, and how does it work? This is a part of an electric circuit. So we have a magnetosphere. Magnetosphere is huge, it has a huge inductance. So it's connected by wires. Wires are magnetic field lines along which a plasma flows. And those wires flow through a small inductance, which is a polar cap. What is going on with the polar cap? Look, the magnetosphere wants to be force-free. I mean, so just in the state with the lowest energy. And it communicates through the circuit that this inductance wants a certain current to flow through it. If it doesn't get this current, I mean, so just try to stop like huge electrical motors. So just you will get an electric shock. Because if it doesn't get this current, a huge voltage develops. And what this voltage does, for instance, if we have like, and here we end up with a classical, so just well-known concept of pair creation. So if there is a mismatch between the current density the magnetosphere requires and the current density which flows through the polar cap, and the current density must be carried by particles, no current density, huge potential drop. We have a one particle, it's being accelerated by the strong electric field, it produces gamma rays decay into electron-positron pairs, those are pulled apart, contribute to current. If it's not enough to split the electric fields, they're being accelerated, produce more pairs, and so it goes on. The question is, how does it work? So just like, the most common model, so just put forward by John Arens at the end of the 1970s, was assuming that the whole process is stationary. So there is a stationary flow of particles. Good. And there is a mouse. Darn. Okay, so just I will skip this, but I will get to the result. So just when I started modeling, what is going on is a polar cap starting from the first principle. So assume basically that the maximal equations are correct. And second, what I got is that under no circumstances this plasma flow is stationary. So it always is a set of discharges which produce a lot of plasma. Then this plasma screens the electric field. Then when this plasma flows away, a new gap appears. Basically, under any conditions, the pair formation is more like Ruderman-Sutherland model, not like an Arens-Charlemagne, even if it had free particle extraction from the surface. Moreover, it turned out that the pair creation is non-uniform across the polar cap. So the results which we obtained like almost a decade ago is that the pair formation in the polar cap is non-uniform and highly non-stationary under any circumstances. Well, what does it mean? So this is a fundamental part, which assumes that we have like a quasi-force-free magnetosphere and that the Maxwell equations are correct. It means that whatever this plasma does, there are some intrinsic periodicities or quasi-periodicities which we should see. And the time ranges are about 10-ish microseconds. So, dear observers, please, if you do study microstructures, please go to those timescales and tell me, are we fundamentally wrong or are we fundamentally right? So, because we must see this. This again, quasi-force-free magnetosphere plus maximum equations. That's a fundamental result which follows from our study. Then the next step, we don't know the radio emission mechanism. And I mentioned that this flow of plasma is highly time-dependent and non-uniform. So what happens is, but the magnetic field is extremely strong. What happens if the particles cannot move across magnetic lines? They can move only along magnetic lines. If you try to separate particles by this intermittent electric field, you're not going to get any electromagnetic mode. You are going to get only electrostatic mode with electric field, which is aligned along magnetic lines. But I mentioned the second part. The pair creation is non-uniform across the magnetic field. It means even particles are moving only along magnetic lines. This non-uniformity does create the component of electric and magnetic field perpendicular to magnetic lines, which can create an electromagnetic mode. So we know, so just from those studies, we know that the pair creation is non-uniform and non-stationary. And there's only those two facts immediately tells us there is a natural mechanism which will work. So just we don't need any additional assumptions for this mechanism to work to create an electromagnetic-like mode in the discharge zone. We do not need to wait until plasma moves away, develops some instability. This instability creates charged bunches, which we have never seen in our simulations. And the distribution function of plasma is such that I don't think that it will allow creation of plasma bunches. It's not like a solid result, but it's more like a common sense conclusion. But on the other hand, so just in the process of creation of plasma, we can generate this electromagnetic mode, and this is a result of particle and cell simulations, where this is the density of plasma, and this is a toy model where we just varied the photon propagation lengths in such a way that the pair formation front is inclined. So magnetic lines are in these directions. This is the plasma density. So the pair formation front is inclined, and here it is perpendicular to magnetic lines. And if you look at those two plots, this shows Poynting flux of those electromagnetic waves. And those waves are generated exactly in the regions where the front, pair formation front, is inclined in respect to magnetic lines. So it does seem to work. So the spectrum of those waves is broadband. So it's, so just at that level, it's consistent with what we see at pulsars, but don't try to press me and ask, can you explain me this? Spectral linears, can you explain me cutoff? No, because what I'm doing, I'm trying to explain how a TV works starting from maximum equations. And so just we have not yet finished the exploration of that particular part in terms of it's last slide. In terms of does this mode really works as a pulsar emission mechanism? Because we have to show whether it can escape this plasma, because it's generated on a very dense plasma, and plasma is keep pouring in, is being created there. But our analysis shows that after some initial exponential decay of this mode, it goes into a linear regime. This is the amplitude of our mode. And after some time, which experience the exponential decay, should look at this maximum, it goes into a linear regime. So just when it decays linearly, then it can survive until the region when the plasma density drops, because magnetic lines are divergent, then it decouples from plasma, and then bingo, we can see. So main conclusions. So starting from the first principles ab initio, now we have quite a reliable global magnetosphere model when we assume that most of the pulsar magnetosphere is filled with dense plasma. And that model tells us that polar caps are extremely important regions, where I would say most important regions of the pulsar magnetosphere. And though in polar caps there is a pair formation which supplies the plasma for the whole pulsar magnetosphere, this pair formation is always non-stationary and non-uniform. And one of the consequences of this is that it seems that it can produce a coherent radio emission, just in the process of plasma creation. Thank you very much.